Okay, good afternoon everyone. Like Dagmar said, my name is Hunter Lockhart, and if you don't mind, I'm going to kind of switch us from the world of geophysics to the world of geology for this final presentation. I spent 6 months, May through November of last year, working on the new ventures team at BHP Billiton, taking a look at the structural and stratigraphic evolution of the Great Australian Bight Basin. Of course, in the context of evaluating the petroleum prospectivity of the region. Just a minor disclaimer, due to the confidential nature of the work that I did, some of the geological ages and formation names are going to be withheld, but the rest of the presentation should be fine. Okay, as of 2 years ago, I had no idea who or what BHP Billiton was, so I thought it would be necessary to kind of give an intro slide. BHP Billiton was formed in 2001 during the merger of Broken Hill Proprietary, which was an Australian oil and gas company, and Billiton, which was a Dutch mining company. The headquarters currently are in Melbourne, with major offices in London, Houston, Perth, and other cities. BHP Billiton has nearly 50,000 employees worldwide, of which 4,000 or 5,000 of those are in their Houston location. And BHP Billiton has primarily been an offshore deepwater exploration company, but now has gained exposure to the unconventional resource plays onshore North America with the acquisition of Petrohawk in 2011. So with that said, today I'm going to give you a brief overview of the Great Australian Bight Basin. I'd like to move on into the structural and stratigraphic evaluation, follow that up with interpretation of gross depositional environments and a few maps that I created with my team, and then finally conclude with some of the key learnings that I had over the course of the 6 months and a few of the results from my study. So as you can see here, we are on the southern margin of Australia. Outlined in the bold yellow is the Great Australian Bight Basin, which is comprised of a number of subbasins within it. My primary focus was over here on the eastern side in the Duntroon Subbasin and in the Ceduna. The Great Australian Bight Basin is defined by the Llewellyn Fracture Zone to the west, to the north by the onlap and pinch out of Cretaceous sediments onto continental rock, to the south by the maximum extent of Santonian rocks that were deposited out onto oceanic crust, and to the east by the Otway Fracture Zone. The Great Australian Bight is a rift basin which developed into a passive margin. The rifting began around the Oxfordian, Calovian, and the mid to late Jurassic, and continued through the Tertiary. The basin itself covers about 840,000 square kilometers. It sees water depths of around 5,000 meters at the maximum extent, with a maximum sediment fill between 5 and 20 kilometers, with the primary deposition in the Ceduna Subbasin out here to the east. There are a number of potential source rocks that we examined throughout the study, including some potential late Jurassic lacustrine mudstones, some early Cretaceous fluvial lacustrine coals and mudstones, an Aptian marine shale, Albian Cenomanian aged marine shales and coals, and finally a Cenomanian Turonian aged restricted marine mudstone. The data that we had available was relatively sparse. Besides regional 2D seismic lines, I had access to 11 offshore wells and 4 wells onshore across this entire area. And one of the challenges of the Great Australian Bight Basin is that today there have been no productive wells and there are no hydrocarbon fields. So just a basic exploration summary of the area. There has been limited success, that's putting it nicely. Looking up here at the top, I basically split all the wells into 2 slides, beginning with the Madura Shelf, the 4 onshore wells and the 1 offshore well. We have Gambanga 1, Air 1, Euclid 1, Apollo, and Malibu 1, which were drilled by a number of different companies in the 1960s and 1970s. These wells all TD'd in basement, and as you can see from the depth of basement, we have relatively shallow sedimentary cover up here on the shelf and onto the continent. There are also a number of wells, which I primarily focused on within the Ceduna and the Duntroon subbasins out to the east. I'm not going to go through the names of all these wells. A lot of them TD'd in the basement and were drilled anywhere from the mid to late 1970s all the way up to 2003. The latest well being Gnarly Knots 1 and 1A, as you can see there, which was drilled by Woodside Petroleum, an Australian company, in 2003. BHP had a drilling campaign in the early 1990s when they drilled Borda 1, Green 1, and Vivon 1. All three were dry holes in the Duncombe Sub-Basin. So my initial work, we had a farm-in opportunity within the Duncombe Sub-Basin, and I was basically to evaluate that with a few other team members on the Australian team. And then a few months after that, we discovered that another company had taken a massive position within the Ceduna Sub-Basin. So we kind of expanded our study to the entire Great Australian Bight Basin. Now, even though there has been no production to date, there are a number of hydrocarbon occurrences within the basin. There are a number of gas shows and potential oil seeps throughout the Great Australian Bight that point to the fact that there is a working petroleum system within this area. About a decade ago, an organization called Geoscience Australia dredged up some high TOC, high HI, Jurassic to Cenomanian rocks within some submarine canyons out here to the far west of the Great Australian Bight in the Bremer Sub-Basin. At a number of these well locations, there have been reported oil and gas shows, which I looked at and examined through the well completion reports. At Jerboa 1, in the middle, as you can see in the Ayers Sub-Basin, there was an interpreted paleo oil column about 15 meters that was intersected in Oxfordian shales. Coal-associated gas shows in Cenomanian silts and sands at Potteroo 1 on the border of the Ceduna Sub-Basin and the Madura Shelf. At Gnarly Knots 1A, the most recent well that has been drilled, there were gas shows with oil inclusions and Coniacian sands. And then at Platypus 1 and Greenly 1, as you can see here in the eastern Ceduna, gas shows in Upper Albion sands, and then reported oil and gas shows within Turonian sands, which upon further examination were basically shown to be dry gas and condensate. And then further out here to the east, there were a number of interpreted oil seeps. Now there are major ports in this area, so we don't know if those were seeps that were associated with a working petroleum system, or if they were associated kind of with superficial oil due to minor oil spills in the area. So optimistic at best. The data that I had access to were a number of regional 2D seismic lines, well completion reports from the 11 offshore wells and 4 onshore wells like I just described. In-house biostratigraphic data, which I'll talk about a little bit later. Numerous published literature, primarily academic, looking at the rifting mechanisms, which I'm going to talk about later in the South Australian margin. Previous work done by BHP in the early 1990s when they drilled those 3 wells in the Duncombe Sub-Basin. And then plate and paleoenvironmental reconstructions, 2 different models that I looked at, both GTEC and SCOTIS has some good recreations that I examined. So, as I said, the objective of this study was to re-examine the Great Australian Bight Basin, focusing on the source potential, because as we saw, that was the key problem with this basin. This included a structural and stratigraphic evaluation and also the completion of a number of gross depositional environment maps. Just up front, our conclusion was that the basin remains too risky, and we think that there's still the lack of a regional source. Expensive wells. The last well that was drilled by Gnarly Knots cost over $200,000, and we expect that today, if we're going to drill offshore and even deeper water, the well cost would be elevated from even there, around $300 million. This is a very challenging drilling environment in these seas. These are some of the roughest waters on the globe. Numerous environmental concerns, and like I said, tough weather. Finally, we think that the basin is insufficiently charged in order to be economically viable, so we're staying away. So first I'd like to begin with a structural evaluation, which I'll basically summarize as examining the rifting models between Australia and Antarctica, because that's still under debate. So initially, my work consisted of a thorough seismic interpretation of the 2D lines that I had access to me, with a focus on the rifting history. Two major observations that I had while going through these data were that I saw a hyperextended continental crust that had been thinned from around 40 kilometers up on the shelf in the continent down to about 5 kilometers, just inboard of the oceanic crust. Also, present-day asymmetry on both the Australian and Antarctic margins, although we had no seismic covering the Antarctic margin available to us. Both of these observations from seismic are explained by a different rifting model, which I discovered upon an extensive literature research. So basically we have two legacy and member models. That is the pure shear model proposed by McKenzie, and finally a simple shear model by means of a detachment fault from a guy named Wernicke. So first I'd like to go over the McKenzie model, which explains that hyperextended continental crust, like I said. Below here is a diagram that you can see of this McKenzie model that has been applied to these Australian and Antarctic conjugate margins. So from this diagram we see a ductile mantle and a deep crust that's been thinned and stretched by a pure shear mechanism and replaced by this upwelling asthenosphere. Above that, numerous growth faulting within this brittle upper crust, which provides for the accommodation of this massive extension. The hyperextended continental crust then leads to mantle exhumation at the continent-oceanic border, and the model results in unobserved relative structural symmetry on both margins, which I did not see after looking at the seismic material. I concluded that this model was not appropriate to apply to the conjugate margins. The other model is the Wernicke model, which explains the structural asymmetry that we see present day. This model is completely different. The mechanism is a simple shear sliding off if we consider the Antarctic margin to be the upper plate and the Australian margin to be the lower plate. This model is asymmetric as compared to the McKenzie model and assumes structural dissimilarity in the evolution of these conjugate margins. This extension is controlled by a low angle detachment fault, as you can see here, that goes within the mantle lithosphere. And then above that we have the removal of sediments which are shed off by this detachment fault as Antarctica begins to slip off above Australia. This model results in asymmetrical geometries with distinct footwall and hanging wall characteristics which are observed on seismic. Finally, there's a preferred model, which is a hybrid of both models, and I didn't discover until late in my project. So I'm going to go through a number of figures here that basically show the structural evolution from this model that's been applied to the Australian and Antarctic conjugate margins. There are 5 stages of extension with this polyphase model, which combine aspects of both the McKenzie and the Wernicke model. This model explains all of the features that are observed on seismic, as well as the present-day structural asymmetries between the two margins. This model begins with pure shear stretching, starting around the Colobian at 165 million years ago, where we have future detachment sites on both the Antarctic and Australian sides on pre-existing basement zones of linear weakness. Following that, in the early Cretaceous, we have stretching and this pure shear model, which is basically extension that is impossible without numerous normal faults. This extension is accommodated by both normal faulting and ductile stretching and thinning of the deep crust. In addition, as you can see from the figure, we have thermal subsidence from the lithospheric contraction following this period of initial extension and high heat flows in the early Cretaceous. After this, in the Cenomanian, we switch from this pure shear mechanism into a simple shear, Wernicke-like extensional mechanism. As I said, the Antarctic margin here acts as the upper plate, with the Australian margin acting as the lower plate. And we have this large-scale detachment on these mobile Albian shales as the late Cretaceous sediments are faulted off with Antarctica on this detachment surface. Finally, this results in mantle exhumation at the COV on the Australian margin. Moving up into the late Cretaceous and the Turonian-Koniacian boundary, we have extension that continues via this detachment fault, continuing as we have upwelling leading up to this future breakup zone between the two margins. And then, as I said, on seismic, we see a lack of late Cretaceous, Cenomanian age sediments because they have been faulted off with this detachment. And they're largely absent on the seismic lines that I observed. Finally, in the Santonian, we have initial oceanic crust at about 83.5 million years ago, which was identified by magnetic striping that I studied. And the Santonian is a switch from this rift phase to a drift phase as Australia begins to fully separate from Antarctica and move up north. This polyphase model leads to the present day asymmetrical structural geometries that we see today. This model conforms with both the initial stretched ductile continental crust and has implications for heat flow, as this hyperextended continental crust going from about 40 kilometers inboard all the way up to 5 kilometers could potentially lead to an over-mature source. And this theory also confirms the mobile Albian shales on which this detachment surface was able to slide off. So now that we've examined the structural rifting history of the Great Australian Bight Basin, I'd like to take a look at the stratigraphic evaluation, beginning with a chronostratigraphic chart for the Ceduna subbasin, which I constructed. I have a chart here for both the Ceduna and the Duntroon subbasins, which was basically created using observations from seismic and well log penetrations, looking at the seismic in a sequence stratigraphic perspective. So beginning down here, the earliest sedimentation that you can see is in the middle to late Jurassic, around the Calovian period, where we have these early syn rift, potential lacustrine rift valley lakes that are formed. Above that, potentially colifaces and continental deposition during the early Aptian and this late syn rift structural period. Above that, we move into a coastal plain facies, as you can see in the green, during the transition from this late syn rift phase into a sag phase, as we have this lithospheric contraction. Following that in the Albian is the first marine flood and a period of major transgression, depositing just above that marginal marine sandstones, moving into deeper water outboard. This continues up until the Cenomanian, when we have uplift of the Gawler Craton to the north on the Australian continent, and the shedding off of sediments and deposition of a massive deltaic sequence, prograding out, as you can see in orange, into deep water facies, just outboard of Gnarly Knots right there. In the Turonian, we have another marine transgression, and then following that, a second massive deltaic depositional sequence from the Campanian to the Maastrichtian. During the Paleocene and at the Mesozoic Tertiary boundary, we have a period of enigmatic uplift, which is not explained in literature, and we couldn't come up for a reason for it. But there's basically non-deposition outboard and potential erosion up on the shelf. Overlying this in the Eocene and moving up to present day, up on the shelf is prolific carbonate sedimentation on a cool water carbonate platform, and then outboard of that we have some condensed basinal marine shales, which were not the focus of our study. Just to the east of that is the Duntroon subbasin, on which I constructed a second chronostratigraphic chart. As you can see from the orange at the base of this diagram, we have widespread continental deposition with potential fluvial deposits, channelized sands, and colifacies all throughout the Jurassic and up to the Aptian. And we have a marine transgression during a period of late syn rift at the Aptian-Albian border, and the first deposition of coastal plain facies in the green, and above that, marginal marine sandstones. Again, at the Albian-Cenomanian boundary, we have massive deltaic sedimentation prograding out past Greenlee 1 well, which is the furthest well outboard that we have in the Duntroon subbasin. Another marine transgression in the Turonian, Kodiakian, and then the second deltaic sequence that continues deposition through the Maastrichtian and Campaign. At the Paleocene, we have a lack of sediment caused by this enigmatic uplift, erosion on the shelf, and marine hiatus within deep water. And then following this, in the Eocene up to present day, we have a third marine transgression, the deposition of more cool water carbonate rocks and condensed basinal mudstones deposited outboard with potential turbidite up there. So now I'll move on to the final aspect of my project, which was creating gross depositional environmental maps, which were heavily based on pre-existing maps by GTEC and SCOTES, but also were created off of these chronostratigraphic charts in both the Ceduna and the subbasin, consistent with seismic observations and rocks present on well logs. So my team and I selected 5 key intervals which we considered to contain potential source rock depositions, beginning with the Berriasian about 144 million years ago, which serves as our model for this late Jurassic, early Cretaceous potential lacustrine source deposition in these early Rift Valley lakes. So as you can see on the top left of the slide, I've included a diagram from GTEC, which basically shows the Australian continent at this time and what's going on depositionally. So in our area of focus, in the black box on that upper left-hand diagram, you can see that deposition here is completely continental. We have no marine influence whatsoever. So below that is the gross depositional environmental map that I created, with continental deposition represented in orange, an uplifted mountain range type provenance where we have the shedding off of sediment providing the siliciclastic sedimentation in the purple. Marshy to coaly facies in the green, with lacustrine Rift Valley lakes represented in brown, and estuarine environments, which is on the further west to this map. Also, I reconstructed the current day lease blocks so we could see where we had deposition of different facies over our areas of interest, along with wells that have rocks of this age present that were intersected. And then finally, we have the Antarctic continental crust, Australian continental crust, and between those two black lines, we would begin to have transitional crust. So the next period that was under consideration was the Aptian, about 118 million years ago. As we have the formation of this Tulabuck Seaway, as you can see, coming in from the northeast, which provides the deposition of the source rocks for the Cooper-Eromanga Basin onshore Australia now. This Tulabuck Seaway was interpreted to not reach the Ceduna or Duntroon subbasins based upon our examination of facies from well logs that we had available. This Tulabuck Seaway introduced open marine conditions if the Southeast Indian Ocean was connected to the Tulabuck Seaway to the northeast, which from our model we do not think was the case. It was the Southeast Indian Ocean was not in communication with the Tulabuck Seaway at this time. As you can see from the map, the facies represented here, we have gas-prone coaly facies that were present at the Ceduna and Duntroon subbasins at this time. And also, we were looking into an alternate interpretation within our area of interest and the Duntroon and the Ceduna subbasins, and trying to link these to rocks on the northwest shelf of Australia, where we have the deposition of a regional source called the Mudarong Shale. During the Albian was the first basin-wide marine flood, which came in from the west and was deposited marine sediments just south of our areas of interest. As I said earlier, the Tulabuck Seaway further up to the northeast was disconnected from this first basin-wide flood. The accommodation that was created was due to thermal subsidence at this time, contraction of the lithosphere, and also elevated global sea levels. These are shallow water conditions within the Great Australian Bight Basin, which potentially allowed rapid sedimentation of organic material onto the seafloor. And then just to give you an idea of the paleolatitude at this time, we're still potentially in a cool climate with paleolatitudes around 60 to 70 degrees south. Moving on, in the late Cretaceous and the Cenomanian, we have the onset of this rapid deltaic sedimentation as the Gawler Craton to the north is uplifted and provides the provenance for the siliciclastic deposition. This is nearing the beginning of unrestricted marine conditions in our area of interest. However, this encroaching marine seaway coming in from the west is not yet fully connected to the encroaching seaway coming in from the east, as you can see from the map of Australia up there on the top left. The Cenomanian was also a period of global thermal maxima and oceanic anoxic environments at the Cenomanian-Turonian boundary. So it's our interpretation that there could be a deltaic source that was deposited at this time, as we have anoxic conditions that would allow preservation of the source. Finally, these deltaics during the Cenomanian could provide both reservoir and seal for the potential underlying source rock of the Burriasian or the Aptian. Finally, in the Santonian, we have the onset of seafloor spreading and the transition to this drift phase. We have the potential for deep water fan deposition outboard of our area of interest in the lease blocks. And then finally, continued deltaic and marine sedimentation prior to the onset of rapid deposition of this Campanian and Maastrichtian delta across the margin. Finally, I'll just conclude it with some of the key learnings that I had over the course of the 6 months and the results from this study. So from the structural evaluation of the Great Australian Bight Basin, I learned that the heat flow from this hyperextended continental crust and the overburden of up to 15 kilometers of sediment in the areas of maximum sedimentation in the Ceduna subbasin could potentially yield to an overmature, deep lacustrine source rock of late Jurassic, early Cretaceous age. From the chronostratigraphic diagram, I learned that the combination of the late Cretaceous rotated fault blocks paired with potential reservoir top seal paired deltaic phases points to the potential existence of structurally and stratigraphically isolated reservoirs and traps throughout this area. Also, that the restricted marine conditions during the Albian and Cenomanian at this time of a global OAE were present for just a relatively short period of time. And because of that, the preservation of a thick and expansive regional source rock is unlikely. Finally, from the GDE maps and from the model that my supervisor and myself constructed, it's possible that marine conditions existed south of the Ceduna and Duntroon subbasins, and from the well penetrations during the early Cretaceous. However, if that were not the case, then the basic prospectivity depends on the deposition and preservation of a younger source rock. So to conclude, the well data that I studied indicates that we have favorable environmental conditions that existed for source rock deposition and preservation. However, the source presence and the deep water is completely model driven. The reservoir presence within the late Cretaceous deltaic section has been proven by previous well penetrations and can be used as an analog for older, unproven deltaic reservoirs. Finally, when considering the likelihood of oil versus gas, we think that there's very good gas potential within our area of interest as proven by the numerous gas shows at the well penetrations. In addition, there could be oil potential, but based upon my study over the 6 months of my internship, the regional source is unlikely to have sufficiently charged the traps. The early cinereous source rocks could have had a very different heat flow based on the rifting model that I proposed, and finally that would lead to economic viability limited to the basin flanks. So with that, I'd like to acknowledge my entire team at BHP Billiton, including Mike Wojcik, Rob Sawyer, Paul McIntosh, Richard Keene, and then the two vice presidents, Niall McCormick and Mike Jameson. And then here at Rice, of course, Dagmar, Dale, and Dr. Dan Baum, Mary Bergen, Liz Ike, my fellow classmates, and Emily Falk, although she's not here. So that's it.
Any questions?
Yes?
What's a paleo oil column and how is it interpreted?
So I might have a backup slide for that. We really didn't pay too much attention to it because it wasn't within the Seduna and Dentrium subbasins. It was further off to the west. Let's see, that was at Pottery 1. If I can go to 52 or 53, I might have information on it. Okay, well, I'm not exactly sure, and I'm not going to go all the way through to slide 52. It was, we don't think that there was sufficient oil within that 15 meters of the core to convince us that there could have been an oil source rock and migration into traps that were formed at this time. So it was speculative at best.
In the your statement of predicting things would be over mature from presumably an excess amount of heat coming into the bottom of the basin, I was a little puzzled because, at least from the direction I was looking here, it looked like the lower plate pulling up and being exhumed often then has a large thickness of continental lithosphere that isn't thinned underneath. It can take away a lot of continental crust at the top, but it doesn't thin the entire lithosphere on that side of the margin. Whereas on the other, so I actually would have expected it probably to be a less heat coming, less anomalous heat coming into the basin on the Australian side, and on the the Antarctic side, where you're pulling a lot of the whole lithosphere out from underneath, putting higher temperature rocks up close to the surface. I would have thought that the extra heat would be on the Australian side, the Antarctic side rather than the Australian side. What was the argument on that?
That might be the case, but just looking at the Australian margin, if you consider we have the basin out here and then the continent up here, if you're really stretching the continental crust out, you would have the thinnest crust outboard, where you might have deep water plays out there, which is what we were looking at. And because of that, you would have higher heat flows within that area under the continental crust and potential magmatic underplating, which would provide this heat that could potentially yield an over-mature source rock out there. But further up towards the continent, you're right. The heat flows wouldn't be as high, so that wouldn't be the problem up there.
So are the sediments out that were over the most extended part of the continental crust, where you're talking about volcanic intrusions and things like that, has that filled in with sediment at this point?
It was filled in with...
I would expect it to be about 15 or 16 kilometers thick if you really filled that all the way up to sea level.
Not on the furthest outboard parts, because you have that detachment fault on the Albion shales. You have the shedding off of late Cretaceous sediment, and below that you have a few kilometers of earlier sediment from the earlier Cretaceous and late Jurassic that were deposited. However, all of our well control was up on the shelf, so that was completely model driven, and we really were guessing at best way out there as you're moving out onto oceanic crust. So.
Okay. Good study.
In the wells that you did have some shows in, I believe they were all in upper Cretaceous intervals. Is that, for those prospects, is that about where the faults die in each of those areas?
A lot of the faults extended up to the lower tertiary boundary with the Mesozoic, and that's pretty much the extent. And some of them extended down all the way below the late Cretaceous sediments, and some of them continued on into the basement of those pre-existing fractures. So there was extensive faulting within that section throughout the Cretaceous and late Jurassic, and then above that in the Tertiary, the faulting was pretty much non-existent.
So were the shows essentially in the first porosity below the regional seals?
They were actually above the interpreted regional seals. So in the latest Cretaceous, Cenomanian, Campanian, Maastrichtian, deltaic sandstone reservoirs.
So you concluded and made it clear throughout your presentation that it's too risky. Is that a convenient conclusion because your internship was over, or has BHP actually moved on?
They actually moved on.
Okay.
There were only two of us in the entire company that were working on this, and another company had come in and I think had a $605 million commit. So they clearly thought there was potential within that basin.
Yeah.
And we examined it, and basically, almost 2 decades ago, BHP had looked at it and walked away after they drilled those 3 dry holes. So we thought, maybe something's up. Let's re-examine the source potential of the basin. We came to the same conclusion that they had 2 decades ago, that it's just too risky, well costs are too high, and we don't think the source potential's there. So we're expecting this other company that bought in to basically begin farming out this data, because they were supposed to have drilled a well last year, and that didn't happen. I just hope they never find anything there, or else I'll be proven wrong.
What you might be interested that 2 years ago, at least, in the Imperial Barrel here, in our section, that area was one of the areas. It's what you were presenting started to sound exactly like what I've seen a couple of other teams do 2 years ago.
That was on the Cooper Eremanga, right?
Data with that.
Onshore on the Cooper Eremanga basin?
Well, ours was on shore. It wasn't ours, but it was another team that actually had the Great Australian Bight with, I think, the same basic 2D data set and a few wells that you were working with.
Interesting. Yeah, I'm excited to see, if anyone does actually drill a well out there in the future. If they find anything. Hopefully if they do, it'll be sizable, but I don't think they will.
Thank you very much.